Yes, we are pleased to present a small project that came about the line impedance and line impedance measurements in the frame of Powerline communications, together with a Swiss manufacturer for AMC filters, Schaffner in this case. And we have a small collaboration on this project that came as a follow-up of the ZNet project we have presented already in this conference earlier. And it's also interesting because this presentation will connect things together with the presentation from Mr. Lutz that we have seen earlier this afternoon. So what I will present shortly is the interconnection, the relation between grid impedance and Powerline communication transmission, the quality, the elements that affect the quality. Then, since impedance has an important role, we will see that the line impedance stabilizer can improve that. So that's a design from Schaffner that we will present. And then we tested that system LIS or component from Schaffner in our laboratory in Sion, and the results were quite positive. Okay, we are University of Applied Science, Western Switzerland, located in southern Switzerland, and we have a laboratory for power electronics and drives, which work now for, let's say, 12 years about grid impedance measurement. We have our own impedance meter, and we have now found interesting application in Powerline communication. As you know, Powerline communication with the, for instance, G3 PLC that is popular in this part of the Europe, send a signal between 34 kilohertz and 92 kilohertz on the grid. The level of signal is limited to a couple of volts by the Senelec standard. But if we connect on the same point, like the smart meter, an inverter, which is switching at frequency maybe 24 kilohertz, you will find harmonics in the same frequency range, switching harmonics in the same frequency range. So there's been big discussion that this is the trouble for Powerline communication. To avoid the signals or the perturbation, the emissions from the inverter, the standard for emission is coming now based on the compatibility levels that have been defined lately. And now we can see in this picture the effect of the filter and where the harmonics are landing. So we need a filter. Now, if you look at the filter, it has a very good attenuation in the frequency range 150 kilohertz to 3 megahertz, for instance. That's where the filter must play its role for normal EMC problems. But what you can see is that depending on the cutting frequency, we'll have resonances. In particular, in this case, one filter we took has a very important serial resonance by 30 kilohertz. So this serial impedance drop down to 1 ohm is in the middle of the Senelec A band for Powerline communication. We have made tests with converters. We have found a converter battery charger that has similar resonance by 40 kilohertz. And when we install this converter, we can see that the shape of the signal over the frequency range for the G3 PLC is dropping down significantly when the converter is connected in parallel to the grid. Actually, you can see that the attenuation of the signals is matching pretty well with the impedance profile of the input filter of the converter. That's one converter. Now, if we check, and that was the work, the collaboration with Schaffner, if we check several filters, we can see that every filter has resonance in different frequencies, and the value of the minimal impedance, if you measure just the filter, no lines, no attenuation, it's extremely low. So if we go in the range of 100 milliohm, I can bet that the signal transmission from the smart meter is very much damped. So Schaffner has decided to try to design a product that can be installed between the loads in the building, let's say in the switching board, and the smart meters that will communicate with Powerline communication signals. And the characteristic or the specification of this product, okay, it's a small size. You can have it connected to the switchboard, and you will pass the line and neutral conductors through 2 separate holes. The impedance on the output, or the impedance of the device, if you measure the device itself, is increasing with the frequency, with a relative high value, 70 ohm in the middle of the Senelec A band. I'm sorry, I just have to switch off a part. Yes. So it's also important that this filter does not bring insertion losses. So and that you have quite a resistive behavior in a larger frequency range, not too inductive, not too capacitive. If you put together with this improved impedance a filter, so there is also a noise reduction. So we might cut a bit off the noise that might come from different appliances in the house. So that's the concept of Schaffner. They put that in the box, and we tested it in our laboratory. The laboratory is based on the HES test bench, where you have 2 devices, communicating device. For instance, here you see the smart meter, and here you see the data concentrator. And the system is separated from the grid with standard line impedance stabilization devices. And then the line is emulated by simply a capacitor with a resistor. And you can affect or change the transmission line by changing the resistor value. So it emulates a long line or a short line, for instance. We can connect then different elements in parallel to the smart meter. Of course, our impedance analyzer, a device to analyze the communication, and then the loads we took, in this case, laptop adapter that works either in this case like PFC mode, so with the rated load here down. So this is a picture of the test setup. You can see that we have here a very simple emulation of the lines with this variable resistor and capacitor. We can also test with real cables to see if this is matching very well to the reality or not. And then, of course, you have this line impedance stabilization network to avoid any perturbation from the grid. And then here, the smart meter on the left, the smart meter here, and the data concentrator on the right. And here on the other side, our computer charger, laptop charger, and the load for the grid. For the measurement of the signal transmission, we use the Neuron N-box, which gives you different analyses. You can see on the vertical axis here the time, and horizontal axis the different frequency packet or slots for the G3 PLC. And the coloration gives you the signal to noise ratio with a good, of course, high signal noise ratio in green. And then there is another, how should I say, indicator for the signal strength, which is RSI, and you can see it by the size of the square dots here. So, for instance, we have here PFC adapter, a filter in parallel to the line impedance stabilizer, and you can see that despite the low signal noise ratio, we still have a quite good communication. Or the opposite, it's not always linked, the noise ratio and the quality of transmission, because the impedance play quite important role here. We have three cases. We have no load, no line impedance stabilizer. Then we had the laptop converter or charger for the second case. And in the case 2, we add the LIS to the device. The last case, we took away the neutral connector here. No, sorry, the protective earth connector to see if it makes any difference with our system. So we measure the impedance with our power analyzer, power grid impedance analyzer. And you can see now in the case without line impedance stabilizer, this resonance by, let's say, 40 kilohertz and about 10 ohm as a result. It's not very deep in this case, but you can see the effect when you connect the line impedance stabilizer in between, that the impedance is much more stable and has higher value on most of the Senelec A band between 30 kilohertz to 190 kilohertz, a very good stable situation. The effect of communication now, the first measurement with the three cases, with the LIS, no LIS, and in between the load, but no LIS. And you can see here the signal noise ratio, depending on the frequency on this axis. And you can see that when you don't have the line impedance stabilizer and the load, you have the worst signal noise ratio. Now, by adding in case 2 the line impedance stabilizer, we can see that things are improving, and despite the load, we have higher values for the signal noise ratio. That was the data concentrator side. Now on the smart meter side, where the line impedance stabilizer is connected, you can see that we have actually a very good situation generally. Of course, no load, no problem. Now you connect the load, and then with the stabilizer, a bit better situation. Finally, we check the communication quality index that is also provided by the neuron box. And we can see here, of course, no load and not much trouble, very good communication on the smart meter and data concentrator. Now we connect the load. The smart meter quality transmission index drops quite significantly. And by adding the LIS, we see that these values are coming back to a normal situation. Maybe a bit less on the smart meter side, but a very good improvement on the data concentrator side. So this is a positive result with this concept. Now Schaffner has developed prototypes, improved the prototypes. I don't know what will be the follow-up for this product, and we did not discuss lately about that, but I think it's very interesting to see that there are some solutions to improve the communication with Powerline communication devices based on the fact that the trouble comes not only from noise, but it comes also from grid impedance in the frequency domain. Thank you for your attention. I hope I did not go too much over the time. And if you have questions, I'm pleased to answer them.
There are two questions from Hamburg, I see. Then first Professor Schulz, then Dr. Do.
Yeah, thank you very much, Professor Rogo, for this nice presentation, also for preparing the slides in German for us. Thank you very much. And I have a question to the Powerline communication transmission quality. That means if you will install this line impedance stabilizer, would it also cover the connection of different Powerline communication devices? You investigated the smart meter connection, but there are also different others, maybe cameras or data transmission over Powerline from local networks, and how influenced the number of Powerline communication devices the quality of the transmission of the transmission itself. Is there a direct relation, or it depends that on the device and on the place on that they are connected then?
Can you repeat the questions? I understood the first part, the last part.
Yeah, my question is, I should now focus maybe in my question, how influence the number of the connected Powerline communication devices the quality of the signal transmission
with the line impedance stabilizer?
Yeah.
We did not come so much forward from this test setup with two devices, data concentrator and smart meter. We had previously in the ZNet project made tests in Tecnalia in Spain, where together with our colleagues from Bilbao, Basque University, and there we had 40 smart meters altogether and much longer lines, and it was the real first prototype from Schaffner, and already there we could notice a slight improvement in the situation with 30 to 40 smart meters. Of course, we should go, and that's not our job. Schaffner should go back. Sorry for the ringing. They should go back to Tecnalia, where we have this very nice test site with many smart meters.
Okay, thank you very much.
Yes.
Okay, there's another question, but first Dr. Do, then Robert Stiegler from Dresden. Mr. Stiegler, I will already enable you to speak. But
so I don't have a question anymore.
Okay, then Robert Stiegler, please.
So hi, Dominique.
Hi.
Thank you very much for this presentation. I have one question. So this is, I could say, a more or less magic device, but so it's decoupling more or less the load impedance from the grid, as I understood. But how is it when you have a look from the side of the load? So is the grid impedance, which the load sees, then also increased? So because I see there's a danger if the load is emitting something that the voltage limits are violated.
That's a good question. I think we have measured also the impedance from the other side, but I don't have that just like prepared for this presentation. I will check that. But yes, you are right. If you increase the grid impedance also from the grid side, you will have some risk of higher voltage on those frequencies. Now, if you look at the profile of this device, we should keep in the low frequency not too high impedance, and the frequency range where the device is really working and active is really aimed at the Senelec A band. But we should check on how is the impedance by 50 Hertz. That's right. I suppose it should not have so much influence. It's an active device with a controller. So you can affect the way the device responds by different frequencies.
Okay, thank you.
Yes, I will try to provide you some measurement if we have.
Yeah, perfect.